is Katrina Mendoza from Mulanay, Quezon, reporting live at Southern Luzon State University, Lukban, Quezon. For today's topic is that we are going to discuss about the Ybus admittance matrix, wherein a lot of fourth-year students are been struggling in finding out what kind of elements, construction, definition, application, and etc. does it have. For the different aspects of the Ybus admittance matrix, stay tuned. Hello everyone, this is Katrina Mendoza, your reporter for today. And today we are going to talk about the Ybus admittance matrix. So I have said earlier that this is going to be a long run, or I have stated that if you want to stay tuned and know more about the Ybus admittance matrix, you really have to wait and see and be with me step by step along the way as we have this roadmap to learning the Ybus. So starting off with the definition, of course, we couldn't know where we are headed to if we don't know the definition of the Ybus itself, and of course the advantages on why did anyone made the Ybus or invented the Ybus, what is the benefits, its application, and of course the construction and elements. We are going to dissect all of it, as well as the circuit solving example. We are going to have this certain circuit wherein we are going to solve for, like for example, our current, what is the given admittances, and so on and so forth. So there are so many jargons to talk about. And lastly, of course, to boil it all down to our conclusion. So here flashing the screen right now is, you can see, is a circuit. We are very much familiar since the very first year of college that as electrical engineering students, we are going to deal with a lot of circuits until the day we die. So we as engineers in the future, we really have to start off working on different complicated circuits. As you can see right now in the screen, it's not that complicated if we are going to dissect it, if we are going to understand every element, every component that is part of it. As you can see, we have different circuits, different constructions of circuit that we may apply the Ybus admittance matrix. So this is an admittance diagram of a tree-bus network. Yung kanina, it is also a tree-bus diagram. And later, papakitaan ko kayo ng two-bus, wherein we are going to have a 2x2 matrix. For 3-bus, we are going to have a 3x3 matrix. So let's discuss that furthermore later. Okay, so starting off for our first destination and second pinagsama ko na. So the definition and the advantages. So let's start. So the definition in the power system of the Ybus admittance matrix is that it represents the nodal admittances of the various buses. So here in the first sentence, we could dissect that Ybus. Okay, there's admittance. That's the reciprocal of the impedance. There would be nodal admittances to be specific, and there would be an interaction with the buses. So with the help of the transmission line, now we are dealing with real power system. So as we are now mentioning transmission lines, buses, which are connected to each other, and also the admittance matrix that is used to analyze the data that is needed in the load, or a power flow study of the buses. So it explains the admittance and the topology of the network. So when we talk about the network topology or topology of the network, it only means that it is the connection, or it is the arrangement of elements, of nodes, of different components in a certain communication network. But here, we are going to analyze or have this matrix as a way for us to analyze the data that is needed in the load or power flow study of the buses. So from the name itself, Ybus admittance matrix. Actually, madami siyang tawag pero we are going to dwell with that later. Pero Ybus. So the element Y, or the significance of the Y, symbolizes admittance, right? Way back in our circuits 2, or the latter part of circuit 1, we had talked about admittance, which is the reciprocal of impedance, or 1 over Z, wherein the admittance matrix or the matrix itself, we have talked about that in circuits 1, way back in circuits 1, wherein meron tayong tinatawag na n by n, or like for example 3 by 3 matrix, 2 by 2 matrix, wherein this serves as our calculation. It serves as our method to be able to like for example in a circuit where we are going to solve for our current. So that current can be solved in a way of a matrix. Do you get me? Going back to our lesson in circuit 1. So the other definition is that it is known to be as the nodal admittance matrix or the admittance matrix, Y matrix, or Ybus matrix. All in all, it has the same meaning or intention of having a n by n matrix describing the linear power system with n buses. So it only means na kung ilan ang number ng buses mo, that will be the number of matrix that is in your linear power system. So meaning say, kanina, we have 3 buses. That 3 buses, meaning to say we have a 3 by 3 matrix as a method to be able to solve for our current, for example. So pag may 2 tayo, 2 buses, we have a 2 by 2 matrix that we are going to use. So it represents the nodal admittance of the buses in a power system. So in realistic systems, which contain thousands of buses, the Y matrix is quite sparse. So each bus in a real system or a real power system is usually connected to only a few other buses through the transmission lines. So that is mostly the fact about the Y bus or the Y matrix method, wherein it shouldn't deal with a lot of buses like for example in the real power system or in the real transmission lines wherein admittances are connected to it. So moving forward to the advantages. So the following are the advantages of our Y-bus admittance matrix. So the first one is that the data preparation of the bus admittance matrix is very simple. Pero looking back at our example, diba, there is a matrix in my first construction. There's a lot, the first part wherein I featured 3 by 3 matrix and different constructions as a gist or as an overview of what we are headed to. Mukha siyang complicated, pero it states here that one advantage is that that's simple. Second is that the formation of the bus admittance matrix and their modification is easy. So the reason why the modification is easy is because the formation is simple. The next one is that the bus admittance matrix is a sparse matrix, thus the computer memory requirement is less. So why is that? Why do we mean by sparse matrix? Sparse matrix is what we call those matrices or a matrix wherein it contains mostly large number of zero values. Bakit pa tayo magkakaroon ng matrix when it is zero, di ba? That's the etiology. But the real thing is, the reason why it has zero values, those large zero values in a matrix will cause a computer memory requirement to consume less. Anong mangyayari when the computer consumes less? It only means that the memory or the frequency of the computer or the processing will be faster. So there's convenience. Diba? The sparse matrix enables a computer or enables us to work faster because it only has large zero values or large amount of numbers containing zero, wherein it applies to consuming less of a power or less of a space, wherein it allows the computer to process things faster. So that is the reason why the data preparation of the bus admittance is simple, or making it easier, and the formation of the bus admittance and their modification becomes easy because most of the value that is in it is zero. Next is the application. Why do we need to use the Y-bus admittance as a method in solving different values needed in our power system? Okay. Now we are going to talk about the load flow in power system. So that's the main focus of our Y-bus admittance. So sabi dito, flash in the screen, is that it provides a method of systematically reducing the complex system to a matrix that can be solved by a computer program. So there are a lot of values that can be deduced from a power system or a complex system in real life, right? There are a lot of transmission lines containing shunt admittances, containing that their main admittances or the admittances connecting to bus 1 to bus 2. What if there are thousands of buses? So this Ybus application or Ybus admittance help us systematically reduce that complex system into a matrix wherein we could use the equations to construct the Y matrix to come with the application, the basic application of the first and second law of Kirchhoff, or Kirchhoff's first and second law, which is the KCL and the KVL, wherein to a circuit with a steady state sinusoidal operation. Okay. Way back in our first year of college, we had basically talked about KCL and KVL. So it's a basic law for each and every one of us, and every engineer could understand, wherein the Ybus admittance had helped us push through keeping things that is complicated or making things complicated into a much simpler system. So most real-world power systems are highly complex and nonlinear. So a sophisticated mathematical method called Newton-Raphson is used to solve for the voltage magnitude at load buses, wherein PQ buses and voltage angle delta at PQ and PV buses in the system. So PV, PQ, and so on and so forth are just designated names. For example, in algebra, the A and B, X and Y. So para bang sinasabi na this is bus 1 connected to bus 2, something like that. So the values of the Y bus matrix are used in the Newton-Raphson equations to solve for V, or absolute V, and the delta. So once the calculations are complete, the values that weren't calculated in Newton-Raphson, or the real power, are calculated manually using the values of the Y-bus matrix. So by means of pushing through the method of Newton-Raphson, because there are a lot of nonlinear and highly complex, sophisticated mathematical method that should be used in the real power systems or the real world power systems, we have to use that as our step 1 and then go to a simpler step or method, which is the Y-bus admittance method. So that is the real life application of the Y-bus. You see how useful it is and how simple it is to be used in power system and how beneficial it is. So without this, we are going to resort to a much more complicated method. So we should thank the inventor of the Y-bus matrix to be able to let us solve easier and faster for the real world power system. Next is our Y-bus construction and elements. So now we are going to dissect our Y-bus admittance matrix circuit. We're going to start off with a circuit, then apply it in our matrix so that everyone could follow and everyone could understand. So let's start. Okay, so now you can see flashing the screen is a single line, and that single line, a vertical line, symbolizes our bus 1. And our bus 1 in real life must be connected to a certain voltage. Now our bus 1 must be connected to another bus, which is our bus 2. And this connection is made by our transmission line. So here we are going to use the medium length. So medium length transmission line has in consideration of what we call the shunt admittance. So the shunt admittance is also known to be as the line charging capacitance of a transmission line. So there are varieties of length for the transmission line, and this is just going to be an example. So our transmission line has this rectangular yellow model wherein it symbolizes our impedance, wherein that impedance can be used to be able to resolve for our what we call as the admittance. Going back to our circuits, latter part of circuit 1 in the beginning of circuit 2 is that our admittance can be deduced from the reciprocal of our impedance, which is 1 over z. So in our example, we have our impedance, which is J 0.8, which is the imaginary part of our impedance, because here we are just going to focus on the reactive component of our impedance rather than including the resistive part of the impedance. Our impedance has this equation: Z equals R plus JX. R is the resistance, J is the imaginary number, and X is our reactive component or our reactance, either be it capacitive or inductive, so on and so forth. So we have to take note of our formula or equation for our impedance and admittance. So I have jotted it down in the lower right of the screen so you can check it. So here, by means of doing the math, 1 over z is equivalent to 1 over j 0.8. And now we have this negative or negated imaginary number, which is j 1.25. So next up is that since sinabi natin that the transmission line in medium length has shunt admittance, so we have to put our shunt admittance in this part. We have this admittance y equals j 0.25 in bus 1 connected to bus 1. And we also have this shunt admittance connected to bus 2, which is it has the same value. And now we're not going to stop with 2 buses yet. We are going to introduce you with another bus, which is bus 3. And this bus 3 is connected to our bus 1 only and not to our bus number 2. And since we have this transmission line, meaning to say we have this another impedance model or another value of impedance, which is here I had designated to be as J 0.5. We're going to solve it for the admittance, or to solve for our admittance, 1 over 0.5j or j 0.5 is equivalent to a negated imaginary number, which is negative 2j or j2, I'm sorry. So after that, of course, since we have this transmission line having a shunt admittance, means to say we should have a line charging capacitance, which is another one connected to bus 1, which is it has a value of j 0.2. Another one, it has a value of j 0.2, is connected to bus 3, and our shunt admittance is ready in that is connected to another transmission line. And of course, let's just finish off our circuit having a symbol of arrow, meaning bus 2 is connected to a certain load and our bus 3 is connected to a certain load because of the reason that they are not connected to one another. So meaning to say, if we are going to look for its impedance or admittance, is that equal to 0 siya. Now we're going to talk about the Ybus matrix itself. Just to be clear, we have 3 buses here. Bus 1, bus 1, bus 2, and bus number 3. So meaning to say, as I've said earlier, that's the first thing that we have to look for. How many buses do we have? Because that's the indication of how many matrix or what kind of matrix we are going to use. So meaning to say 3, so we have a 3 by 3 matrix. So we are very familiar of the look or the appearance of our matrix, right? Since it was discussed way back in our circuits 1. So here we have 3 by 3 matrix. So meaning to say, vertically we have 3 components and horizontally we have 3 components as well. So our Y11, just to explain every admittance that is flashed here. So we have Y11. Our Y11, meaning to say, is that all the admittance that is connected to our bus 1. So this admittance here, this admittance here, and this admittance here are all connected to bus 1. Next, our Y12. So the only admittance that is connected or connecting bus 1 and bus 2 is this admittance here, which is negative J 1.25. Next, our Y13. This is Y13. So the only admittance that is connecting bus 1 and bus 3 is this one. Moving forward to Y21. Our Y21 is bus 2 and bus 1. What is the admittance connecting bus 2 and bus 1? This negative 1.25. So it's just the same as y12. So y22, so here comes another complicated part. Not so complicated, but it is just the same as y11. So y22 is all of the admittances that is connected to our second bus. So this bus 2. So we have this and we have this. So J 0.25, it should be added to negative J 1.25. And since there is no connection to bus 2 and bus 3, there are no admittances to be considered in that part. Next, Y23. As I've said earlier, there is no connection, so meaning to say that is equivalent to 0. So Y31, so we have a bus 3 and bus 1, and all of the admittances that is connected to that we will consider. But yet we only have this admittance connecting bus 3 and bus 1. So that's negative J2. And next we have this Y32, as I've said earlier, same as Y23, we don't have a connection, so that's equivalent to 0. And lastly, we have an admittance to Y33, and all of the buses that is connected, or all of the admittances rather connected to bus 3 will be considered or added, or their algebraic sum will be the value of the admittance of Y33. I hope you all get that. That's basically how we change the matrix the matrix to having values based on the circuit that we have. Okay, it's somehow pretty much simple at this state. So now, as you can see, this is our circuit that we have done, and I just added the designation of V1 in bus 1, V2 at an angle of a certain value in bus 2, and same as in our bus 3, because later, if we're going to construct the whole matrix, that we are going to need the value of the voltage. But I'm assuming that I am going to use 230 at an angle of 0 for our V1, and 220 at an angle of 0 in our bus 2. And in bus 3, the voltage would be, I think I would put it to 250 at an angle of 0. So that's going to be our values, and later I will go and flash that in the screen for all of you to understand it well. Now, as you can see, there is some type of oblong and indication in our Ybus matrix. So that oblong part, or all of the components Y11, Y22, and Y33 are called or dubbed to be as our diagonal admittances. So this diagonal admittances, as you can see, they have some type of characteristic. Now, all of the admittances connected to, like for example, bus 1, and then bus 2, then bus 3. So there's a lot of admittances to be considered and to be added, right? As for our Y12, Y13, Y23, Y21, Y31, and Y32, all of those admittances, in short, all of those admittances that does not belong to our diagonal admittances is known to be as off-diagonal admittances. And that admittances, for me, based on my understanding and based on the textbook or manual, is that this type of admittances only considers to be multiplied in -1 always. That will always be negated or multiplied by -1. And usually our Y12 and Y21 always have the same values, but still you have to take into consideration in double checking. But I guarantee you that in the end of the result is that the value of the admittances of the off-diagonal admittances is negated or is multiplied to -1. Okay, next stop. We're almost there. The Ybus expectation. So this quite important because this will deepen our understanding with the Ybus admittance matrix. It will allow us to understand more on what we are expecting of what we are headed to and why do we really need to know more about the Ybus admittance, especially when it comes to power system analysis or in data preparation for that type of analysis. Okay, now let's start. So now we are just going to consider two buses, okay? I have introduced these elements and constructions to you. Tinanggal ko lang yung bus 3. And now we are going to use what do you call this? Parang symbols or designations. Like, for example, we have Y1, we have YA, and we have Y2. So yung ating Y1 is the first shunt admittance connected, and the second shunt admittance is the Y2. Okay, as I've said, our shunt admittances are line charging capacitance. So it will always be there to be considered when there are presence of shunt admittances and presence of medium length transmission lines. Okay, it will vary along the way in different circuits as we have different construction of circuits, different types, and different connections. Okay, moving forward. Now, why do we have this arrow pointing from bus 1 to YA and this arrow going down? Okay, now going back to our lesson in circuits 1, wherein the KCL and KVL, or KCL just to be specific. KCL is the Kirchhoff's current law. So meaning to say that the current entering is equal to the current that is leaving. So the same goes here. Our bus 1, the injected current will be equivalent to the current flowing where the arrow wants it to be. As you can see, the arrow is pointing to the right and pointing down because there are some paths where the current could flow into. Okay, so we are just basically refreshing our idea with the KCL that the current entering is also equal to the current that is leaving. Same goes to our I2, as there is a current that has been injected to the node coming from bus 2. So there is two current paths wherein the current could flow through. Our YA, just to clear it up or give you some clarification, that is the same Y12, okay? We have bus 1 and bus 2, and that admittance, the model in the middle, in the transmission line is equivalent to the admittance of Y12. Now we must take note that our impedance has this equation V over I. It's simply like looking for the value of the resistance. So if we are going to look for our admittance, which symbolizes this Y, is that it is equivalent to 1 over Z, or the reciprocal of our impedance. Now, if we are going to look for our current, what would it be? It says here that it's V over Z. Saan yun nanggaling? It has been deduced from the formula of our impedance, which is V over I, wherein we're just going to do some math or rearrangements where we can deduce the formula V over Z. But Z is equivalent to Y at some point wherein Y is equivalent to the reciprocal of 1 over Z. So in the end, if we are going to change that, 1 over Z times V is equivalent to Vy. I hope you understand what I'm saying, but it's basically just math rearrangements and deducing a formula from another formula, so we can catch up with that. We have to remember that I is equals to V over Y, because later our matrix is we are going to solve for I equals the Ybus and will be multiplied with our voltage. That's why I have designated the values for our voltage along with its angles. Okay, now we are going to solve for or create an equation based on I1, I2, and I1 and I2. Dalawa lang pala yung ating buses here. So I1, just to make it simpler, why is it is equal to Y1 times the V1 plus YA times a V1 minus V2. So basically, to solve for I, we have to look for V and Y, diba? As I've said here, based from the deduced formula. So our I1, as we have said, is going to flow here and going to flow here. So starting off with this part, we have Y1. Y1 and V1, since our I1 came from bus 1. So we are going to multiply Y1 with V1 plus, since we have said I1 or the current entering is equal to the current leaving, we have to still add it to another current that had flown through here from bus 1 to bus 2. So based on that, our YA, it has an admittance that is between bus 1 and bus 2. So that YA will be considered and multiplied with our V1 minus V2. Then Y, diba, in mesh currents, in different in nodal, in different types of equations or methods that we are using. Basta it is connected to two buses or into two sources, is that we have to subtract it from one another, the voltage, right? Because that voltage, this is not only the voltage to be considered. We have to subtract it to the other voltage or source that is affecting our first current. I hope you are getting that, but basically that's the gist, or that's on how we are going to create the formula. So simplifying it, we are now having y1 times v1, and the distributing ya, we have plus ya times v1 minus ya times v2. So that's our first current. In the second current, it's the same. It's the same. So we are going to just analyze the data based on KCL, that the current entering must be also equal to the current that is leaving. So our total current is I2, and now we are going to add up the two current that is flowing from our bus 2. So ang I2 natin is here, which is Y2 times our voltage in bus 2, and also our YA, but now we are going to multiply it with the difference of V2 and our V1. Okay. Now, after our equations have been simplified, we are now going to construct it or put it in our Ybus admittance matrix. So basically, it's like the formula or the equation for looking for our current, which is I equals y yv or vy, or y times v. So basically, that's the whole concept of remembering our formula for our current. So here, we are just going to have a 2x2 matrix because we only have two buses. So we have to remember that the number of buses will indicate the number or the n by n matrix that we are going to use as a method in our Ybus admittance matrix. So here, as you can see, what I1 and I2 will be equivalent to our Ys or admittances, then times our voltage. So this is what you call the Y1 and plus YA because it came from this equation in I1. You're just going to focus based on what line you are deducing components. Diba? I1 natin is this equation. So meaning to say, we have to remove the V's there because of the reason na may V na tayong i-multiply dito sa tabi niya. So, Y1 plus YA, but our second, kasi di ba if you're going to make a matrix, this is going to be V1 and this is going to be V2. So, meaning all the components na may interaction or is a part of another component V1 and V2, yun yung arrangements natin. We are clearly aware of that. So now we are just going to put Y1 plus YA since they have both V1. Now we have this V2 over here wherein this is yung part ng may V2. So that's negative YA. Diba I have said earlier na if you are going to interact with, like for example, Y11 to. So yan, there's a addition of admittances that is going to happen. Now here in the Y12, this part na to, Y12, sabi ko sa inyo, i-multiply siya with negative 1, right? Negative 1, then times the value of our admittance. And then earlier, here as you can see, Y12. Our Y12 is negative because I've said earlier that we have to remember that it is always negated or it has a negative sign since it had been multiplied to a negative 1. So same goes dun sa ating Y21. Our Y21 is just equal to the value of our Y12. And now our Y22 is Y2 plus YA. Why is that so? This is V2 and this is V2, so that's Y2 plus YA. Okay, moving forward now, I believe we are almost there. We only have two destinations to go to be able to fully understand our Ybus admittance circuit or Ybus admittance matrix rather. So now this is the Ybus circuit solving sample. So upon knowing all the expectations that that the Ybus admittance matrix comprises, is that we are now dealing with solving an example of a certain circuit or inputting values. Kasi kanina we are just using designations or symbols or like Y1, Y2, and YA. And now we are going to use certain values for us to really understand on how to construct a certain matrix and solve for our current by means of using our Ybus admittance matrix. So let's start. So this is the latter example wherein pinakilala ko sa inyo yung elements and constructions, and now we are going to deal with the values. So as you can see, may mga values na and all of the impedances. Pag impedance ang given, you have to solve for the admittances by just reciprocating it, and the calculator is there. It is easier to compute it with that. Of course, we're dealing with imaginary numbers. So our Y11, sinabi ko sa inyo na lahat ng connected sa bus 1 is that yun yung ating yung algebraic sum nun, or the sum of all the admittances connected to bus 1 will be the value of our Y11. Okay, so starting off with bus 1, we have it here, the admittance here connected in bus 1 and bus 2. We have negative J 1.25 and add with our shunt admittance J 0.25 added to another connection here between bus 1 and bus 3, which is negative J2 plus another shunt admittance connected here, which is J 0.20, which is equivalent to negative J 2.8. I believe that I haven't stated that this part is also connected to bus 1 as well, but I just want to clarify that it is connected to our bus 1. Same as here, since bus 1 is connected to bus 2 and bus 1 is connected to bus 3. So, apat yung admittances natin na kailangan i-add to solve for our Y11. Okay, now solving for our Y12. So our Y12, as I've said earlier, it has to be multiplied by -1. Tapos yung value natin ng admittance that is connected to bus 1 and bus 2. And that's only negative J 1.25. That's the only admittance that is connecting our buses 1 and 2. So if we're going to multiply that with -1, we are going to solve for a positive J 1.25. Okay, now as for our Y13, is that it is also the same. We only have to multiply it with -1, and that -1 will be multiplied to the value of our negative J2, which is the value of the admittance between bus 1 and bus 3. So next up is our Y21. Our Y21 is the same value ng ating Y12, wherein it only had been multiplied to -1. Y22 now is all of the admittances, or the sum of the admittances that is connected to our second bus. So our second bus has this and has this, which is -1 J 1.25 plus our J 0.25. It has no connection between bus 2 and bus 3, so that is the reason na hindi siya kasing dami ng admittances that had been added, unlike our Y11. Next is our Y23. Our Y23 is equivalent to 0 if multiplied with -1, because there is no connection with bus 2 and bus 3. And Y31, same value ng Y13, which is J 1.25. Our Y32 is also 0 because there is no connection between the two buses aforementioned. And Y33 is all of the admittances connected to our bus 3, which is negative J2 and also J 0.2, which is the shunt admittance between here. And that is equivalent to negative J 1.8. Okay, now we are going to assign voltages. So our voltage here in bus 1 is 230 at an angle of 0 degrees. Bus 2 is 220 at an angle of 0 degrees. And our last bus, bus 3, bus 3 is equivalent to 250 at an angle of 0 degrees. So as I've said earlier, we really have to remember this formula I equals y times v, because that's going to be the construction of our y bus admittance matrix. We are almost there, guys, so you have to focus. So now, as we have said that this is the following values of our components, y11 to y33. So we are just going to input them here in our formula, or in our matrix rather. And that is, so this is the values that we have deduced from the formula that we have done so far in our the admittances that we have deduced from our circuit. So after that, we are now going to look for our I1. So I just wanted to clarify pala. See, our Y11 is designated here in this matrix. So that's negative 2.8 here. Our Y12 is designated here. Our Y13, that is J2. Then our Y21 is 1.25. And our Y22 is negative J. And 0 ang Y23 natin. Y31 designated here, that's J 1.25. Y32 is 0. And our Y33 is negative J 1.8. Okay, now moving forward. Okay, now moving forward to our calculation of I1, I2, and I3. So as you can see, we have placed all of our admittances in their proper designations based on their symbols, or Y11, Y22, Y33, and so on and so forth. So now, as you can see here, balik tayo sa concept ng ating matrix. Our matrix, di ba, sabi natin, we are going to designate it here, here, and here based on their similar connected unknown value. Kunwari, pero here, known value natin ang V, okay? So this is for V1, this for V2, and this for V3. As you can remember, di ba, we are going to designate the matrix. Kunyari, we have 3I1 minus 3I2 minus 3I3. Tapos, yung other equation is i-group natin ulit yung components or per term nila based on I1, I2, and I3. Okay, so that is just the concept of the matrix before. And now we're going to apply it again. So as you can see here, our negative J2.8 is here in V1. So the value of our V1 is 230. So we have to multiply it to 230 at an angle of 0 due to the fact that Y times V, or admittance times the voltage, is equivalent to a current. So that current na masasolve natin here is just a partial part of our first current. Okay? Next, para mabuo natin, kailangan natin mag-solve ng dalawa pa because we have 3 components of our admittances. Okay, next is J1.25. J1.25 is in V2. The value of our V2 is 220. So multiply it, another partial part of our I1, or another partial current. Next stop is our J2. This J2 is in V3. So V3 is 250 at an angle of 0, multiplied by that. And now adding all of this will now gain to a result of our first current. And doing the math, we are now resulting to a 406 at an angle of 90 degrees ampere. Now, moving forward to our second current. Second and third current, basically, ganun din yung gagawin natin. All of the values of the admittances must be multiplied to our voltage. That is the reason why pinapatandaan natin na I equals to VY or YV, because that is the formula that we're going to use along the way in our Ybus admittance matrix. So, J1.25. J1.25 is multiplied with 230 at an angle of 0, negative J 220 times 220 at an angle of 0, and 0 times 250 at an angle of 0. And doing all the math over here, ito negative to because negative J, diba? We have to add it all up, pero adding that will cause the positive operation to become negative or to subtract it. So Along the way, in calculating for this equation, we are going to yield with the result of 67.50 at an angle of 90 degrees. Next up with our I3, same process. J1.25 times 230 at an angle of 0. 0 times 220 at an angle of 0 degrees. And negative J 1.8 multiplied with 250, which is our third voltage at an angle of 0 degrees. So, why is it negative ulit? Because of the reason na negative ang J 1.8 and our operation na positive will become negative or subtraction. So, yielding to a result of 162 at an angle of negative 90 degrees ampere. So, you have just to perform the operation. We're like going back to circuits 1 or circuits 2 where we are dealing with imaginary numbers and adding all of them, wherein the difference is we're just focusing on reactive component of our impedance, okay? So it's pretty basic at this point because we are just using a 3x3 matrix. And now we are going to move forward to our last stop, which is our conclusion. Okay, paulit-ulit ko nang sinasabi because actually this is just the concept for us to remember in a Ybus admittance matrix, and this Ybus admittance matrix wouldn't be put into consideration without deducing a formula from our impedance formula. So our current is equivalent to Ybus times our voltage, or I current times our is equivalent to the product of our admittance and our voltage. Okay. Now, just for the final conclusion overall is that we have to make a highlight or clarification or just another round of reminding you the difference between the diagonal admittance and the off-diagonal admittance. So, okay, the diagonal admittance, sabi natin yung sa matrix, yun yung paganon. Lahat ng values na nasagi ng diagonal. So, that is also called the self-admittance. So, it is termed to be as a self-admittance as it is the sum of all the admittances connected to a particular bus. And I have stated that earlier, and we have to remember na lahat na konektado na admittance doon sa bus na yon. Like for example, for Y11, meaning for bus 1, all of that, the sum of that will be the admittance for Y11. Next, hence, the diagonal elements essentially tells us that the total current that is injected into that particular bus. So it only pertains, nasabi ko nga, based on the KCL or Kirchhoff's current law, is that all of the current that is entering is equivalent to the current that is leaving. As for the off-diagonal admittance naman, it is known to be as the mutual admittance. So this is all the admittance na wala doon sa line ng diagonal, or wala, that is all the values that is outside of the diagonal. So that is the mutual admittance, and it is also multiplied by -1. Therefore, it is negated admittance between the two buses, diba? Always our diagonal admittance, nakukuha natin siya, kunyari, ang Y12. It is between two admittances, and it is always negated, multiplied by -1 to be able to arrive to a certain value that will be considered as our Y12. Hence, it tells us that the currents flowing from one bus to another bus, basically off diagonal, is just the admittance connecting two buses. And just to end up this whole report and this conclusion, you have to remember that diagonal addition causes the sum of the branch currents flowing from each node of the network to equal the total current injected into that node. So that concept concludes our Ybus admittance matrix. KCL, everyone, the current that is entering is equal to the current leaving, and we must always remember all of the notes or all of the reminders, especially this formula, I equals Ybus times V, or simply I equals admittance times our voltage, and we are safely going to arrive with the values that we need in the Ybus admittance matrix. And also the application of the Ybus had helped us through years, as this had became or paved way for us, or paved way for engineers to calculate easier for our power system analysis, especially when it comes to data preparation. So that will be all for today, everyone. Thank you so much for listening. And if you have any questions, you can find me at Katrina and Mendoza at slsu.edu.ph. And again, thank you so much for listening. Until the next time, we are going to tackle another lesson. And always remember to stay positive and always look at the bright side. This is Katrina Mendoza signing off.